students, today is the last lecture of the transition and inner transition elements, and today we are going to see the actinoids. The actinoid series, or which is also called as 5F series. What are actinoids? The series of 14 elements after actinium in which last electron enters in 5F orbital. It's called as the 5F series or actinoid series. Series of 14 elements after actinium means in actinoid series actinium is not introduced. Elements after actinium is called as actinoid series. In this series or in these elements, last electron or differentiating electron enters in 5F orbital, that is the n-2, that is 5F orbital, and hence which is also called as 5F series. Why it is called as actinoid series? Properties of these elements are similar to actinium and hence called as actinoid series, and which is at the bottom of the periodic table, but group of actinoid series is the 3 and period is the 7. It is placed in third group and 7th period, and for convenience it is placed at the bottom of the periodic table. This is the actinoid series and this is the lanthanoid series. Its position of the actinoid in group 3 and period 7. Then the elements of the actinoid series. I have not made any sentence, you made any sentence, or there is no necessary to remember the elements sequentially. But see, the first element actinium. Actually actinium is not in the series, but properties are similar to actinium with atomic number 89. Second is the thorium, atomic number 90. Then protactinium, uranium, neptunium, plutonium, uranium, then neptunium, plutonium, americium, curium. After curium, berkelium, then californium, einsteinium, fermium, mendelevium, nobelium, and last one is the lawrencium. Starts actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. Starts with the atomic number 89 and ends with the 103. Protactinium 91, uranium 92, neptunium 93, plutonium 94, americium 95, curium 96, berkelium 97, californium 98, einsteinium 99, fermium 100, mendelevium 101, nobelium 102, and lawrencium 103. These are the atomic numbers of these actinoids. As these are from thorium to lawrencium. These are the inner transition elements or the F block element, but actinium is not F block element, it is from the D block element. Nearest inert gas of these actinoids is the radon, which is having the atomic number 86, and configuration of the actinium is radon, that is the configuration of radon with atomic number 86. Here, as it is D block elements, it is no electron in the 5F 0 6d1 7s2 6d1 7s2 5F 0 6d1 7s2. In case of actinium, it is expected that in thorium electron should enter in the 5F orbital, but actually it is observed that in thorium also electron not enters in the 5F orbital. Therefore, observed configuration of thorium is, I am writing only outer configuration without radon, 5F 0 6d2 7s2. इथं ऍक्च्युअली आपल्याला अपेक्षित काय 5F मध्ये इलेक्ट्रॉन जायला पाहिजे, पण इलेक्ट्रॉन ऑब्झर्व काय झाले, इलेक्ट्रॉन 5F मध्ये जात नाही, तरी सुद्धा आपल्याला इनर ट्रान्झिशन म्हणायचं आहे. ए ब्लॉक म्हणतोय इलेक्ट्रॉन इथं 1 च्या ऐवजी ते किती झाले, 2 इलेक्ट्रॉन झाले. 5F च्या ऐवजी कुठे गेला तो 6d मध्ये गेला. अँड देन इलेक्ट्रॉन स्टार्ट्स फिलिंग फ्रॉम द प्रोटॅक्टिनियम. प्रोटॅक्टिनियम मध्ये 5F इलेक्ट्रॉन्स फिल करायला सुरुवात होते, पण इथं F च्या ऐवजी प्रोटॅक्टिनियम मध्ये 1 च्या ऐवजी किती इलेक्ट्रॉन जातात, 2 जातात. इथं कन्सिडर करायचं की जर 1 असतं तर इथं इलेक्ट्रॉन किती गेले असते, 2 गेले असते. 5F2 इथं 2 इलेक्ट्रॉन आल्यामुळं इथं काय आलं 6d1 7s2 5F2 6d1 7s2. Then for uranium 5F3 6d1 7s2. Then for the neptunium 5F4 6d1 7s2. For plutonium, पुन्हा प्लुटोनियम नंतर इरेग्युलरिटी. प्लुटोनियम मध्ये 5F5 आपल्याला अपेक्षित आहे, पण ऍक्च्युअली प्लुटोनियमला 5F6. We are expected that there should be 5 electrons in the 5F orbital of plutonium, but actually there are the 6 electrons in the 5F and no any electron in 6d, and hence configuration becomes 5F6 6d0 7s2. From plutonium regularly, then after 5F6 5F7 6d0 7s2. Then aquarium, it is, if regularly filled, then there should be 5F8, but as half-filled orbitals are more stable than incompletely filled, there is also 5F7 6d1 and 7s2. This is the curium is the central element in the actinoid series, like the gadolinium in the lanthanide series. Configuration is the same, similar for the gadolinium and the curium. In gadolinium, it was 4F7 5d1 6s2. In curium, it is a 5F7 6d1 and 7s2. This is the configuration of curium. And then beryllium. इथं आपल्याला 5F अपेक्षित होतं, इथं किती 5F9 अपेक्षित आहे आणि 5F9 असणार, परंतु इथं 5F7 6d1 होता ॲटॉमिक नंबर मी ते. beryllium 5F9 6d0 7s2, and from berkelium onward 6d0. I have 10, 6d0, 7s2. I have 11, 6d0, 7s2. Einstein. Then fermium, 5f, 12, 6d0, 7s2. Mendelevium, 5f, 13, 6d0, 7s2. Novelium, 5f, 14, 6d0, 7s2. And Lawrencium, last one, 5f, 15 होऊ शकत नाही. Therefore, there is a 5f14, and one electron enters in the 6d, 6d1 and 7s2. As 5f orbital is completely filled, the electron enters in the 6d, and configuration is the 5f14, 6d1, 7s2, similar to lutetium. That is, in lutetium 4f14, 5d1 and 6s2. Thus, but in case of, it is somewhat difficult to remember, but I think electronic configuration of actinium is not very important. Remember the electronic configuration of curium, lawrencium, protoactinium, and in general electronic configuration of the actinoids is radon, general configuration, radon 5f 1 to 14, 6d 0 1 आहे 2 आहे, that means 0 to 2, 7s2. General configuration of actinoids is 5f1 to 14, 6d0 to 2, 7s2. Only protoactinium, only in thorium, electron is not present in higher orbital, but there are the 2 electrons in the 6d orbitals. And this is the electronic configuration of the actinoid series. General configuration may be asked to the exam. Then properties of the actinoids. Our most common oxidation state of the actinoid is the +3, similar to the lanthanide. It also shows the +3 more common oxidation state. But in case of actinoids up to plutonium, it also shows the higher oxidation state like the +3, +4, +5, +6, +7, etc. In some elements, it shows the higher oxidation state, and after plutonium, it has the stable +3 common oxidation state. Only novelium has the +2 oxidation state. Thus, for actinoids, in short, +3 is common oxidation state. Up to plutonium, it also shows higher oxidation state up to 7. After plutonium, it shows the +3 oxidation state, and novelium has the +2 also oxidation state. Then properties of actinoids. Properties of actinoids. Most of these elements are not found in nature. Not found in nature. That means they are synthetic or man-made elements. Transuranic elements. Transuranic means after the uranium. From neptunium to the lawrencium. These are the transuranic elements. These transuranic elements are synthetic elements or the man-made elements, means which are not obtained in the nature but which which are prepared in the laboratory. Thus, most of the elements are not found in nature, but these are the man-made elements. The half-lives of the uranium and thorium is the highest. Half-lives of the uranium and thorium have long half-life. For thorium, it is about 1.4 to 10 raised to 10 years. Thorium 232, and for uranium 238, which has 4.5 to 10.9 years. As thorium and uranium has large or long half-lives, they exist in the rocks. As thorium and uranium has high long lives, they exist in the rocks. Means only uranium and thorium occurs in the nature because they have half long lives. They are, and all elements are radioactive. From actinium to lawrencium, from thorium to lawrencium, all elements are radioactive. They have high densities, high melting point and high boiling point. High melting point, boiling point, densities. They are less reactive than lanthanides. They are less reactive. Lanthanides react with the water to form lanthanide hydroxides. Actinoids also reacts with the water to form actinide hydroxides, but lanthanide reacts with the cold water and actinide reacts only with the hot water to form the actinoid hydroxides. The +3 oxidation state is common for the actinoids. Also, actinide shows a +2 to +7 oxidation states. Similar to lanthanides, the actinides also shows the contraction called as the actinoid contraction. That is, from actinium to lawrencium, as atomic number increases, the nuclear charge increases and atomic or ionic radius steadily decreases from actinium to lawrencium, and which decrease in atomic radius with increase in atomic number in actinoid series is called as the actinoid contraction. But in case of actinoid, contraction is more than the lanthanide. Why? Because in case of actinoid, last electrons enters in the 5f orbital, and these 5f orbitals are poor shielding effect than the 4f orbitals. As shielding effect is poor, attraction between the nucleus and outer electrons is more, and therefore contraction in the actinoid is the more than the lanthanide series. Some of the actinoid ions shows the color, and this color are the deep color than the lanthanide, and color of the actinides is due to the FF transition similar to the lanthanides. Color due to FF transition. In lanthanides also color due to FF transition. In actinides also color due to FF transition. But in actinides, some actinide ions are deeply colored. Lanthanide ions are fairly colored or paint colored. These are some properties of actinides. All not found in nature. Transuranic elements are man-made. Half-lives of the uranium and thorium is high, hence which are found in the rocks. All the actinoids are radioactive, which have high melting point, high boiling point, high density, which are less reactive than lanthanides. As they react with the hot water but not with the cold water. Actinoid contraction, like a lanthanoid contraction, that is the atomic or ionic size decreases from actinium to lawrencium. Color of the actinoids due to the FF transition. These are some properties of actinoids. Then applications of actinoids. No more applications in the books. Applications. Actinoids are applicable mostly in the nuclear reactors and nuclear weapons, as they are radioactive. They emit the radiations and hence used in the nuclear reactors and the nuclear weapons. Shastra madhe, the one more use is the THO2 with, that is the oxide of thorium with 1% oxide of CO2. Cerium. This mixture is used as a major source of indoor lighting, as well as is used in the outdoor lighting or the camping. Means this is used in the lighting, indoor as well as the outdoor. This is the applications of the actinoid. Then some similarities between lanthanoids and actinoids. We have to say similarities and differences. What are the similarities? Question may be asked on the similarities as well as differences on the lanthanoids and actinoids. Both the series shows the +3 oxidation state common. This is the one similarity. Then in lanthanoid, last electron enters in the f orbital. In actinoids also last or differentiating electron enters in the f orbitals, means f orbitals are filled gradually. F orbitals filled gradually in both lanthanoids as well as actinoids. Both shows decrease in atomic as well as ionic radius, that is contraction. In lanthanoid there is a lanthanoid contraction. In actinoid there is a actinoid contraction. This is the similarity. Both have the low electronegativity, and lanthanoids and actinoids, top to bottom electronegativity goes on decreasing. Lanthanoids also have low electronegativity. Actinoids also have low electronegativity. And the nitrates, perchlorates and sulfates of all these elements are soluble. Nitrates, perchlorates and sulfates are soluble, while the hydroxide, fluorides, carbonates are insoluble of lanthanoids as well as actinoids. These are the similarities in between the lanthanoids and actinoids. Then some differences or dissimilarities. Differences between the lanthanoids and the actinoids. In lanthanoids, +3 oxidation state is common, but mostly +2, +3, +4 oxidation states are possible. But in case of actinoids, +2, +3, +4, +5, +6 up to +7, that means +2 to +7 oxidation states are possible. That is, the more oxidation states are possible in case of actinoids. Lanthanoids do not form complexes, that is coordination compound, do not form complexes easily. but actinoid can form complexes easily with ligand. Can form complexes. Lanthanides do not form oxocations. Oxocations means cations with oxygen. Do not form complexes. Not form oxocations. It can form oxocations like UO plus, UO2 plus, PuO2 plus or PuO plus means this can form the oxocations. Most of the lanthanides are fairly colored. Most of the lanthanides are colorless. But some are the colored which are fairly, that is faint colored. And actinoids are deeply colored. Actinoids are deeply colored. Lanthanide contraction is less while actinoid contraction is more. Why? Because in case of lanthanide there is a shielding effect of the 4F, but in case of actinoid there is a shielding effect of the 5F, and 5F has poor shielding effect than the 4F, and as more shielding effect, contraction is more. These are the differences in between the lanthanides and actinoids. In case of lanthanides, which shows the +2, +3, +4 oxidation state. In case of actinoids, from +7 to +2 to +7 oxidation states. Lanthanides do not form complexes. Actinoids can form complexes easily. Lanthanides cannot form oxocations, but actinoids can form oxocations, that is the cations with oxygen. Lanthanides, most of the lanthanides are colorless, but some are the colored, but which are the fairly colored, and actinoids which are colored are the deeply colored. म्हणजे नंतरचे बाद में के एलिमेंट को बोलते हैं पोस्ट एक्टिनाइड. थोरियम actinoid series start with the thorium atomic number 90 and ends with the atomic number 103. 90 to 103 is the actinoid series. Post, that means after the actinoid series, means from 102 to 118. Atomic number 102 to 118 are called as the post-actinoid elements. That means these post-actinoid elements are transition elements. And these elements, these are the transuranic uranium नंतरचे हे सगळे एलिमेंट आहेत, hence which are the man-made element or synthetic element, and which are radioactive elements also. And as they have short lives, half-life is very short, they have short lives, it is difficult to study their chemistry as they have short lives. This is the last point of the transition and inner transition element. एक गोष्ट लक्षात घ्या, या टॉपिकमध्ये तुम्हाला 3D एलिमेंट, ट्रान्झिशन एलिमेंट मधले 3D सिरीजमधले सगळे इलेमेंट्स, त्यांचे ॲटॉमिक नंबर, कॉन्फिगरेशन लक्षात ठेवायचे. ट्रिक तुम्हाला दिलेले, त्याच्यावरून ऑक्सिडेशन स्टेट कॅल्क्युलेट करायच्या, डायमॅग्नेटिक पॅरामॅग्नेटिक ओळखायचं, आणि त्याच्यावरून तुम्ही ते ओळखू शकता. लॅन्थॅनाइड आणि ॲक्टिनाइडमध्ये मोस्टली 100% म्हणू शकत नाही, मोस्टली हे डिफरन्सेस किंवा सिमिलॅरिटी ह्याच्यावरती क्वेश्चन असतील. ॲक्टिनाइडच्या कॉन्फिगरेशनवरती क्वेश्चन असण्याची शक्यता कमी आहे. जनरल कॉन्फिगरेशन विचारलं झालं तर विचारलं जाऊ शकतं, परंतु कलर्स, ऑक्सिडेशन स्टेट, इलेक्ट्रॉनिक कॉन्फिगरेशन मेनली कशावरती असतील, 3D एलिमेंट्सवरती असतील. Okay, thank you. In next lecture we have to discuss some questions.